Hi, my name's Joe Mitchell. I'm going to speak about approximating maximum independent set for rectangles in the plane. The maximum independent set problem in general in a graph is a notoriously hard problem, both to compute exactly and approximately. In planar graphs, there's a p-task, but in general, in graphs, the best approximation factor is n over log squared n. And no polynomial time algorithm with approximation better than n to the 1 minus delta is known unless p equals np. We're going to speak today about geometric instances of maximum independent set where there may be special structure that will help us do better. So the graph is given as the intersection graph of a set of geometric objects like disks or squares or fat regions, pseudodisks. The particular problem today is that of axis-aligned rectangles. It's a basic geometry problem. Given a set of bodies in the plane, find a maximum cardinality subset that's pairwise disjoint. For rectangles, the input might look something like this, and we're seeking a subset of independent rectangles like this. So a lot of work has been devoted to approximation algorithms for geometric instances. If the objects are disks, or more generally so-called fat regions, there's p-task is known. Here we're talking about rectangles where there's a QP-task, quasi-polynomial time approximation scheme, but the best polynomial time algorithm has a log n approximation until this paper. So here we're focusing on getting a constant factor approximation that runs in polynomial time. So one way you could do this is to resolve a conjecture that's been out there for a while, that any set of disjoint axis-aligned rectangles has a subset, a constant fraction size subset, that admits a so-called perfect BSP, or also known as guillotine separable. And this simply means that there's a cut, an axis parallel cut that doesn't penetrate any of the rectangles, and recursively on each side of it, such cuts exist until you have a single rectangle per face of the binary space partition. This example in the middle shows it's not always possible to do that. Here, there's sort of a cycle of skinny rectangles, but a constant fraction subset, 3/4 of them, does admit a perfect BSP. So the main ideas in this paper are, first of all, we're going to generalize cuts from just axis parallel lines to cuts of constant complexity. And the regions that we get then are not necessarily just rectangles, but there'll be other shapes, what we call corner clipped rectangles, CCRs. We're also going to generalize from binary space partition to a K area. So K area with K at most 3. So we might partition into 3 subpieces. And there's going to be a charging scheme that will allow us to prove our structure theorem that we can afford to discard a constant fraction subset so that we get what we'll call nearly perfect Ccr partition. Once we have that, it's straightforward to use dynamic programming to optimize over all such partitions. So first of all, some notations and preliminaries. The input is a set of n rectangles, assume they have integral coordinates. B will be the bounding box of these input rectangles. A segment sigma penetrates a rectangle that intersects the interior of it. It crosses a rectangle if that intersection is interior to sigma. And this sets up some of our notation. So corner clipped rectangles are basically, you start with a rectangle and you clip out, you remove some or all of the corners. So there's many different corner clipped rectangles, but they're all of constant complexity. The ones that we'll need today are just these. So rectangles and these sort of L-shaped corner clipped rectangles, one corner clipped. I also need the notion of maximal rectangles, where each rectangle is expanded as large as it can be while not penetrating the interior of any other rectangle. So you can always transform K disjoint rectangles into K maximal disjoint rectangles. For instance, start with these rectangles, expand upwards, to the left, to the right, and downwards. And you'll get a set of rectangles, each one in a face that is a maximal rectangle. Now, once we have maximal rectangles, I'll define a nesting relationship. The rectangle R is nesting to the left if his left boundary is interior to the right boundary of an abutting rectangle like this blue rectangle here. And so each rectangle can be classified as being horizontally nested, which I color red, vertically nested, I color blue, and those that are not nested at all will be gray. Now, why maximality is important. If you have maximal rectangles, then this rectangle cannot be nested above and also nested horizontally. So it's either going to be nested vertically or horizontally, but not both. If they were not maximal, then that wouldn't necessarily hold, that this rectangle is nested vertically and horizontally. So the nesting concept is useful because if R is not nested, let's say to its left, then there's going to be a feature, a corner C, that we charge R to, because if we have a cut that crosses R, we're going to discard R and somebody needs to pay for it. And that somebody will be a feature, a corner like C. So Ccr partition is a recursive partitioning initially of the bounding box of all the input. Each face will be a Ccr, and a cut will consist of a constant number of horizontal and vertical segments that partitions into at most 3 subfaces. We'll say it's perfect if none of the input rectangles are penetrated by any of the cut portions, and each leaf has exactly 1 input rectangle. Now we're actually going to relax that a little bit and speak of nearly perfect Ccr partition, where we allow a constant number of rectangles, at most 2 per vertical cut portion to be intersected. So here's some examples of k-area cuts. A binary cut, k equals 2, partitions a Ccr into 2 sub-Ccrs. A k equals 3 area cut partitions into 3 Ccrs. So here's the Ccr partition where at the first level cut is in purple, the next one is in red, then blue, then green. And all the faces are Ccrs. And here's a nearly perfect Ccr partition of these blue rectangles. You'll see some of the vertical cuts cross at most 2 of the rectangles, or penetrate at most 2 of those rectangles. The structure theorem says that if I give you any set of k interior disjoint axis-aligned rectangles within the bounding box, then there is a nearly perfect Ccr partition on a subset of size omega k. Okay, so any set of disjoint rectangles, you can keep a constant fraction and have a nearly perfect Ccr partition. Then the algorithm is going to be based on dynamic programming, where the subproblems are defined by Ccr faces, Q, which have constant complexity, and they're nearly perfect, so there might be at most 2 rectangles that cross or are penetrated by a side of this subproblem. And then we optimize over all possible k-area cuts, k at most 3, so there's only a constant number of things to check, and you get the recursion that sets up a maximization in terms of so-called eligible k-area Ccr cuts, and sums the number of independent rectangles in each of the subproblems. So that leads to the main theorem that there's a polynomial time constant factor approximation. Now, the proof of the structure theorem relies on some more terminology. So again, let's start with what might be an optimal set of rectangles, R1 through Rk. Take their maximal expansions, call that set I prime. And I prime can be partitioned into red, blue, and gray according to nesting horizontally, vertically, or not at all. Okay, as in this picture. Without loss of generality, since it's a partition, you can assume that the number of reds is at most half. The reds and blues can't both be more than a half since they're disjoint. So the number of non-reds is at least half of the total. So our goal is to keep a constant fraction subset of those maximal rectangles in that set. And if we can find a CCR partition that's nearly perfect with respect to the maximal expansions, then the original rectangles, one per expansion, will also satisfy the near perfect CCR partition. So we start with all of the rectangles as being active. And then during a process, the proof process, some of the rectangles are going to be discarded and they'll be removed from active status because they're crossed by, say, a vertical cut line. And a charging scheme will make sure that we don't discard too many rectangles and we keep at least, say, a quarter of them. So the process of cutting, we start with the bounding box of all the rectangles. We recursively partition. If a face has more than one rectangle, we'll partition it with a cut into at most 3 subfaces. And we have to be able to show that we can always do this to prove our structure theorem. And the properties that we require for the structure theorem is that any horizontal portion of a cut, remember, consists of horizontal and vertical subsegments. Any horizontal one does not penetrate any rectangle. It can go along boundaries. It will go along what we call fences. Vertical portions, however, like sigma here, can cross some of the rectangles, and those will have to be paid for. And it can penetrate some as well. It penetrate at one of its ends, at the top or at the bottom. And so there's at most 2. That's where the 2 comes from. So we need a notion of being exposed. A rectangle R is exposed to its northeast, northwest, southeast, southwest, according to whether a horizontal ray from a point just inside that corner penetrates a rectangle or not. So here there's a penetration, here there's a penetration. So this rectangle is exposed on its northeast corner and on its southwest corner. Now, when you make a cut, so if this is a portion of a cut, this sigma, it crosses some rectangles. Those will have to be paid for. But once we cross those rectangles and we'll discard them, it exposes some other rectangles, R1, R2, R3 in this case. And what we do is we establish a fence. A fence is going to be a protection device, a horizontal segment attached to the boundary. This, of course, because this was a cut, this is now a boundary of a new subproblem to the right and to the left of the cut. And we establish these fences. I color them red or blue, depending whether they're anchored on the left or the right, so that we will protect these rectangles that are exposed from ever being crossed, because we're going to make sure that all of our vertical cut portions never cross a fence. Fences become constraints. So when we make a cut here, the newly exposed rectangle R establishes a fence along his top edge, the corner that's becoming exposed, and we extend it one more rectangle over, let's say. Later we'll extend it more than one to improve the constant factor, but say his neighboring rectangles R sub R. So we go 1 over. So we extend the fence a little bit further. And the fence invariant that we establish throughout the process is that for any face Q and any rectangle within it, if it's exposed to its left or to its right, then there is a fence that protects that rectangle, that exposed rectangle, from being penetrated by a vertical cut. And in fact, it extends to its through its right neighbor or its left neighbor to protect its neighbor as well. So here are the initial fences for the initially exposed rectangles. The ones labeled R are initially exposed on in the bounding box B of all the input. And the key technical lemma is just that if you give me any CCR face Q, it's like this one, and it has some set of fences anchored on its right sides, left sides, these red and blue horizontal segments, no matter how you draw those, you can always find a valid cut, a cut that partitions it into at most 3 CCR subfaces, with the property that the horizontal portions go along fences and the vertical portion does not cross any of the fences. The fences are considered constraints. You can't penetrate them vertically. So now you just have to look at some cases. If you have a rectangle, you may or may not have a separation between the red and the blue fences. If there is a separation, great. If there's not, then in both cases, we come up with a way of partitioning it. So here we've partitioned it into 3 subrectangles, here into 2 CCRs. In the remaining cases, I focus on a I break into cases according to this rectangle shaded gray. That's the rectangle that's containing the shifted point, this reflex corner of the CCR, in a vertical decomposition of the red and blue segments within the CCR. And if that gray rectangle touches the top and the bottom, then it's very easy, 1 cut and you're done. If it on the bottom is on a blue and on the top is at the top of the bounding box, then in both cases, again, there's a valid partition into at most 3 CCRs. If it's symmetrically touching the bottom and a blue, then again, easy to get partition into CCRs. And in this case, where it's above is a blue and below is a blue, then we sort of sweep until some other event happens. And now, again, it's easy to get these partitions into at most 3 CCRs. If the top is on a blue and the bottom is on a red, which is the last of the cases, then again, you can partition into at most 2 CCRs. So that's the proof of the technical lemma. Now, fences, remember, provide us protection. We make sure that we never cross a fence with a vertical portion of a cut. However, a vertical portion of a cut can penetrate one rectangle on its top or bottom. It will not cross, or rather, those that it does cross, these rectangles will have to be paid for. Okay, we won't try to pay for the penetrated ones, but the crossed ones. So all of the non-red rectangles that are crossed by vertical cut segments have to be paid for. The red ones we don't care about. Remember, non-red ones are at least half, and those are the ones we're focusing on. So again, there's some cases. If this is the rectangle being crossed and here is his neighbor, then depending on the relationship between his neighbor to the right and symmetrically to the left, and R, here they're flush at the top, and you establish a fence going through R sub R as well as his neighbor. This can't happen because of maximality. That can't exist. Here, the only difference between case 1 and 3 has to do with the whether the bottom is above or below the bottom of R. Otherwise, they're identical. And in cases 5 and 6, the top of the right neighbor of R is above the top of R. And then the corner that we charge might be this corner here. This guy cannot exist in a maximal set of rectangles. So the charging properties, no corner is ever charged more than once. If we charge a corner of a rectangle, then that rectangle has not been previously crossed by a cut, and it will not subsequently be crossed by a cut, because the fences are established. And at most, 2 corners of a rectangle are charged, because we're only charging it from one side. After that, it becomes anchored and there's a fence to protect it. So accounting for this, red rectangles, they're those that are uncut when cut. Non-reds are uncut and cut. Those are the ones discarded and have to be paid for. And our goal is to show that the remaining ones are at least a quarter. Now, every one of the non-red rectangles that's cut, we charge, we pay 1, and we send half a charge to the left, half to the right. Those go to corners that are charged. Each rectangle is only charged on one of its 2 sides. Each of the 2 corners charged 1/2, so at most a charge of 1. So the total amount of charging is the number of crossed non-red rectangles, and the total amount of charge is at most the sum of the uncrossed. So that inequality, together with the assumption that we made at the beginning without loss of generality, gives you that the number that remain is at least this. Clear the fractions, and what you get is this. And that's the proof of the main theorem. Can we do a better factor? Well, originally I had a more complex case analysis with more CCRs, and it was a factor 10. Here we just gave a simple factor 4. With a small variant of this, you can improve this by just having fences go a little bit further and doing a little more care, and you get 10/3. That improves to 22/7 and eventually to 3 plus epsilon. In fact, you can do even better. So there's been recent progress that you can get 2 plus epsilon approximation. You may have seen that just recently presented at SOTA. So the idea is that we're going to use CCRs more generally. This was the original intent of this approach, was to try to explore the question of whether this might lead to a PTAS or not. So can we significantly improve the running time? I don't know. Weights, that's the version I'm currently working on to get improved approximation for the weighted case. Higher dimensions I haven't worked on. That's open as far as I know. And the conjecture, the original conjecture is